Hello again, this is Tim Baldridge, and I'm going to talk about a function today that I learned about just a little bit ago. It would have been a week or so ago, someone mentioned on the Clojure Slack channel, what would you ever use this function for? And I can't even spell it. I would call this Seque or Seque, maybe? I would call it Seque, except we already have Seque of S-E-Q. I had never even heard of this function. I never knew this function existed. In fact, I've still never used this function. But I read the doc string and I thought, hey, that's pretty cool. There might be some times when I could use that. And then I got thinking, you know what? Let's do a tutorial about this. Let's go and dig into this and see exactly what it does. So I'm going to hit Alt-Dot here. And it says, this creates a queued seek on another presumably lazy seek S. So S is the argument here, right? The queued seek will produce a concrete seek in the background and can get up to n items ahead, right here, ahead of the consumer. N or Q can be an integer n buffer or an integer of n buffer size, or an instance of Java util concurrent blocking queue. Note that reading from a seek CQ can block if the reader gets ahead of the producer. So that's interesting. Let's do something to see what we get here. So let's do print as created, and this is just going to be a basic range type thing, right? In fact, you know, this is a good example of how to write a lazy seek function, or at least this is how I write it. Created X, and then we're going to do so this is going to look a lot like range. And as soon as I actually undo my, there we go, print as created 0 to X, and then we're going to have another arity here. That's this would be max. Let's just name variables with actual names. How's that? And so then we have current and max. And then what we have here is we say created current, and we cons cur onto a lazy seek of inc cur and max. Now this won't actually ever stop, because all we do is really pass max along. So we can say if cur when cur is less than max, right? And we'll move the println in here. Okay, cool. Let's get in the right namespace, and then we'll give this a try. There we go. So we can do we can actually just print this println. Print as created, and we can do 10. And let's see, don't know how to create a seek from long. That's kind of interesting. So we do print as created max. Lazy seek. That's actually should be correct. Let's look at our stack trace. And our stack trace says, see a little bit of debugging here, right? And so the problem is in one, this is all internal code. Let's find the first case of, here we go, 13, line 13. And then we go to 13 here. Huh, that's interesting. So what happens if we just return this? That might be something with the printing. I don't know that I did something right there. Don't know how to create an iSeek. Print as created, max, 0 to max. Oh, yeah. So this is how you build lazy seeks. It's been a long time since I've built one, so that's why I'm a little rusty here. Okay, so here we go. Print is created. So lazy seek, it delays the rest of this body. It doesn't execute this body until you call next on the first thing, right? So if we just do print as created and do first, we get created 0. And then when we do next, next then first, it loops through once, right? So this recurs, and then we get created one, and so on and so forth. So we've made ourselves a range. Now, why didn't we use range? Well, range is a little bit weird. Range is a little different, as we've talked about in some of the other tutorials. So we're gonna hold off trying ranged on that on this quite yet. So then we're gonna have here is we're going to do something like this. We are going to do thread sleep. And let's say this took a while, right? Let's say it took 200 milliseconds each time we did this. And then we do print is created 10. And we see we have this delay, right? The sequence takes a while to read. So now we can do print as consumed. And this is going to be a seek of a thing that accepts a seek and slowly reads from it, right? Do seek s item in s, right? So we're going to do seek. We are going to println got this thing I, and then we're going to thread sleep for 200. Now it should take twice as long now to execute both of these, because we're sleeping at 200 at each end, right? Print as consumed. So we do this. Oops. Unable. Oh yeah, we gotta do this. There we go. And so we see it's taking even longer, right? And we can even time this. So when we run time on this, we see that it took 4 seconds, or all told, right? And that makes sense. We have 2 sequences, that's 40 milliseconds per item. We have 10 items, so roughly 4 seconds. Now, according to this thing, according to this doc string, right? Such a weird word, Seque. We should be able to do this and get it in 2 milliseconds. Sure enough, 2.4, close enough. Because according, and we can see the interleaving here, right? The interleaving that's happening is that in the background, if we go in here, in the background, this should be creating a future or a thread or something. You know, and we can see here, if we see anything along those lines, I would expect to see, oh, here we go, send off. An agent of all things. That's kind of interesting. I would have not expected this to use an agent. But let's take a look at it. So the first thing we do is we're creating a blocking queue. We see if we were given a queue. If not, we create a blocking queue of a certain size. Linked blocking queues, you cannot get nil. So they create a special object here that is a filler for nil. So we never start with nil because that signals the end of the sequence. Okay? So we get a lazy seek of s. Makes sense. And then this is an error handler. So drain. Okay, so this is the output side of the thing. We're just going to reason about this. The output side of the thing is this drain. And what this does is it has a lazy seek of taking one item. If the item that we took is the queue. Okay, so it's saying when we get to the end of the list, we're going to send the queue itself through the queue. And that's signals the end. So if that happens, we are going to see if there's any errors on the agent, and then we're going to return nil. Just so this is like our when here, right? When you're creating a lazy seek, if you're all done, you just return nil. So let's go back here. So we would return nil in that case. Otherwise, we're going to send to the agent something called fill, a function called fill, and then we're going to release pending sends. Not exactly sure why we need that. We should look at what that does. And then we just cons on to the value that we got. And we recur. So you see here this drain is in a lazy seek. Now there's two ways of going about creating lazy seeks. I tend to put the cons on the outside of the lazy seek. They're putting it on the inside. Doesn't really matter. It doesn't really matter because this just calls drain and then drain calls lazy seek. So it doesn't matter. I think my version here, where cons is on the outside of the lazy seek, by default would always create one item, right? You can see that here. If we just do print as consumed 10, and we don't do anything at all, we just return this thing as nil. Let it be garbage collected. Oh, so not print as consumed. Print as created. And we just, 10 items. We're always going to have one created. If we were to swap these around, and let's do that a little bit. Let's just for the sake of showing this. If we do this, then the first item is never created. Because this lazy seek delays the body, right? So in our method, the cons is on the outside. We always create the first cell, and we say the first cell is created by default, the next is delayed. And in this way, it's swapped around. The first item is never created, and we only create the first cell if required. Don't really know that it matters. Sometimes it's nice to have some, when you first call this thing, the seek is set up correctly and that you got a item in the seek. But whatever. Okay, so let's look back here. So what we're doing is we have this agent, and we're sending basically whenever we want a new item in the agent. We want a new item in the queue. Right here, this take. Whenever we want a new item, we're just calling fill, sending this function called fill to the agent. So what does fill do? So fill apparently takes a argument, which is the previous state of the agent. So whenever you call send off to the agent, you have the previous state. So what does this do? When we have a previous state, we execute this body. Okay, so when we're all done, and we're all done executing the seek and everything, the sequence, then we're just going to set the agent's body to nil, apparently. Or return nil here. So if S is an exception, if the state is an exception, then we're going to just log an error. And logging an error tries to put the error into the queue. That's kind of interesting, it looks like. I would not have expected that. So then we have here is we're destructuring the seek, right? We get the first item. And once again, we're saying if S, then we're going to put the value into the linked list. And then we're going to recur to get the next item in the seek. And we're going to offer that. Okay, so this is starting to make a little bit of sense. What we're doing is, there's some weird mechanics here. What we're basically doing is using the agent as a synchronization primitive. And that we're going to try to lazily offer items into this queue. And when we can't anymore, when the queue is full, link blocking queue is full, we're going to stop, and this agent is going to pause. And then once we take all the items that we can from the queue, we send off again. So this is kind of a version of lightweight threads, kind of. But what we're doing is we're explicitly releasing the thread here for this agent. There's no thread sitting around the entire time, right? That would be one way to build this, where you have a thread that's just sitting there, taking up memory the entire time. This releases the thread, which is kind of a cool approach. I like that. Okay, so we do print is created. Okay, so this is working, right? Now, and actually here I'll show you a hack. We get some weird. We're getting some weird code here because it's all interleaved. See, so we have created for and so forth. If we do it this way, with print IO, I mean this IO is single threaded more or less, right? I mean that. Two things can't actually physically be writing at the same time to the same place. So what we do instead, the problem is that println with multiple arguments is going to print these items one at a time, and that's why they get interleaved. So this is a cool hack. If you use string and then you print, it's printing a single item. And there we go. Although we would need to flush, wouldn't we? I bet if we do this, this would be fine. Println also flushes the output stream, which meant we didn't get any feedback till it was done. There we go. That's a little better. Okay, cool. I didn't know if that would work without having the new line. Okay, so there we go. So we create 0, 1, 2, and so forth, right? We create a bunch, and then we got some, and created and got some, and so on and so forth. Okay, so let's see. How else can we do this? Let's say that we have 20 items. So apparently we can give this an integer, right? We can say this can go 10 items ahead. So let's say that it took 100 milliseconds to create them, but it takes 200 to consume them, right? We never get too far ahead here, right? We create 19, and we only get 3 or 4 items ahead. So according to this, we can give this a size of, like, let's say 20, and say, hey, we can create them all first. Like, the creator can run way ahead, and we'll just buffer them in memory. And I have my arguments in the wrong order. So according to the docstring, this should allow us to create way faster. And it didn't do it a whole lot, did it? Maybe let's make a bigger time difference. So 4 times faster. Let's see. There we go. That's what we expected to see. So we ran way ahead. In fact, if if this was more like 1 millisecond, and we run this, they create almost instantly, and then our reader is slowly reading them. Now, from what I understand, this can cause problems with what do you call it? Chunked seeks. So I want to try that real quick. So if we have 200 and 200 here, what I'm going to do is we're going to try to do something that's a chunk seek. And let's see what seek of range 20 is. Type. What's the type of this? It's a long range. Fantastic. That's not helpful at all. So if you do map identity, does this turn into a chunk seek? No, it's a lazy seek actually. Let's see. It's always hard to try to figure out how to get a chunked seek. Okay, so that is a chunk seek. But map isn't. So when does the map deal with chunk seeks? Let's see, because there is some code here. Maybe we don't need to call seek on that initially. Does map not actually produce a chunk seek? Let's see. Well, let's see if we can cause a problem here anyway. So, if this is chunked the way it should be, mapped X. Let's do our little hack again. And then we take 1. There we go. Yeah, so it is chunked, although it said it wasn't. So if you're not familiar with it, Clojure has this optimization called chunk seeks, where if you say like this, take 1, in some cases it will take a whole bunch of items and process them much more efficiently. They're in chunks of 32 items actually. So we only took 1 item from this, but it actually generated 30 items, right? So apparently we can have a problem here if we try to do something like this, where we do thread sleep 100, and this is where we would get a problem, is that this is going to, before we get our first item, that this is actually going to take us, let's do first. Yeah, but this actually took us 3 seconds to get the first item, right? Because this is chunked, and I don't think well, Seque might be able to help us here. Yeah, I mean, that converted it to a Seque, and so it completed almost instantaneously. But if we put this on the other side, and we say we only want it to run ahead 2 items, it's still going to run ahead 30-something items, right? Before it returns the first thing. So I'm not exactly sure that that's a huge problem. I'm trying to think of when I would actually experience this or a problem with this. You would just basically need to be careful if you were super sensitive to that sort of thing. Okay, so that's a lot about that. So why would we use this, right? How is this useful? Well, I can see this being useful if you had like if you had a something that was reading a line. Not that read line. But basically, if you had a, let's say you had a CSV file, right, and you're reading the rows in one at a time, this would be a very simple way to just allow the disk reader that's reading in data to run ahead a certain number of items. Right? I can see this being useful in a lot of the situations where you have some I/O, you're reading something from the disk, you're reading something over the network, and your code is more or less single-threaded. Right here, there's nothing about this code that looks, like it's single-threaded. But what you could just say is, hey, run this back-end thing on another thread. Now you might say, don't we have PMAP, right? Well, sure we have PMAP. The problem is that PMAP executes the function itself in a separate thread. But it doesn't necessarily execute the walking of the collection in a separate thread. So, I mean, yes, we could combine these and do PMAP fnx and say process x and return x and do thread sleep 100. So if we put this all together, right, let's do 200 there. Let's allow this to run ahead 20 items. So this is 600 milliseconds for each with, so 12 seconds, is that right? Never do math while you're recording a video. That's a good way to make a fool of yourself. But whatever, we'll see what happens here. So here we're creating and processing, so on and so forth. And 6 seconds is our final time, because we're actually doing this processing in a separate thread. If we just do map, what's our time? Eight seconds. So PMAP is a good way to run the transformation in parallel. And there are some problems with PMAP, which maybe we'll cover later. But it works. A lot of times it just works. And CQ or Seque or whatever you want to call it, CQ, we'll call it that, CQ. You can have a little accent in there, CQ. But the way it's designed, it's for consuming in parallel the sequence. PMAP is transformation of the sequence in parallel. So we actually have 3 sets of threads. We have the consumer, we have the processor, and we have the creator. So that's more than you probably ever wanted to know about this function, and this a little bit longer video today, but I thought it'd be cool to kind of sit down and walk through it and just kind of go through the way I would play around with this sort of function and debug it and think about it. And diving into that code was an experience I haven't. Like I said, I never even knew that function existed. It's wild. It's been in there since Clojure 1, and I have never seen it. Now you could say that would be a reason to never use it. I don't know. I'll probably use it at some point when I'm writing some batch script and I just need some fast performance improvement out of my system. But anyway, hopefully you found the tutorial today interesting, and thank you so much for watching.